Good morning, respected ma'am, Dr. Savita Rati, and all my friends. Hope so all are good at home, and it's my request to all please stay at home and be safe. Myself, Kirti, roll number 5423, class 5.8. My presentation topic is Hausdroffness and nets. Abstracts of my presentation is introduction, Hausdroffness and nets, definitions, examples, propositions, limits of nets, limitations, references, and some external links. Firstly, we are discuss about nets. The purpose of the concept of a net, firstly introduced by E. H. Morey and Herman L. Smith in 1922, is to generalize the notion of a sequence. In mathematics, more especially in journal topology and related branches, a net or Morey-Smith sequence is the generalization of notion of a sequence. In essence, a sequence is a function with domain, the natural numbers, and in context of topology, the codomain of this function is usually any topological space. However, in the context of topology, sequences do not fully encode all informations about a function between topological spaces. In particular, the following two conditions are not equivalent in general for a map F between topological spaces X and Y. The map F is continuous in the topological sense. Given any point x in X and any sequence in X converges to X, the composition of F with this sequence converges to f of X, that is continuous in the sequential sense. Now we discuss about definition of nets. Let A be a directed set with order relation greater than equal to and X be a topological space with topology T. A function f from A to X is said to be a net. If A is a directed set, we often write a net from A to X in the form X alpha, which express the fact that the element alpha in A is mapped to the element X alpha in X. A subnet is not merely the restriction of a net F to a directed subset of A. See the link to page for a definition that we given in the last slide. Now, examples of nets. Every non-empty totally ordered set is directed. Therefore, every function on such a set is a net. In particular, the natural numbers with the usual order form such a set, and a sequence is a function on the natural numbers. So, every sequence is a net. Another important example is as follows. Given a point X in topological space, let Nx denotes the set of the all neighborhoods containing X. Then Nx is a directed set where the direction is given by reverse inclusion so that S greater than equal to T if and only if S is contained in T. For S in Nx, let Sx be a point in X. Then Sx is a net. As S increases with respect to greater than equal to, the point Xs in the net are constraints to lie in decreasing neighborhood of X. Now we discuss about the proposition. Closedness is equivalent to containing all net limits. Let X be a topological space. Then a set A contained in X is closed if and only if all nets X lambda belongs to del, so that for all lambda belongs to del, that is X lambda belongs to A, which converges to a point X belongs to X. We have X belongs to A in A. Suppose first that A is closed and that X lambda, that is lambda belongs to del, is a convergent net in A to a limit X. Suppose X does not belongs to A. Then for all M contained in Nx, we defined N belongs to del so that at least Xn belongs to M, which implies that M intersection A is not equal to phi and X belongs to curl A. Since x belongs to M, x does not belong to A. Since a set is closed if and only if it contains its boundaries, we conclude that x belongs to A. A contradiction. Suppose then that A contains the limits of all its convergent nets. Then let x belongs to curl A and note that n bracket x is a directed set ordered by inclusion. For each m belongs to n, choose x m belongs to A intersection m by definition of curl A and observe that x m belongs to n forms a net converges to x. Thus x belongs to A, and since x was arbitrary, curl A belongs to contained in A and A is closed. Limits of nets. Let f if x alpha is a net from a directed set A into X, and if Y is a subset of X, then we say that X alpha is eventually in Y or residually in Y. If there exists an alpha in A, so that for all every beta in A with beta greater than alpha, the point x beta lies in Y. If x alpha is a net in the topological space X and X in an element of X, we say that the net converges towards X or has limit X. And write limit x alpha is equal to X if and only if for every neighborhood U of X, X alpha is eventually in U. Intuitively, this means that the values x alpha comes and stay as close as we want to X for large enough A. The example net given above on the neighborhood system of a point X does indeed converges to X according to this definition. Now, Hausdorff. Hausdorff. Hausdorff was a German mathematician who is considered to be one of the founders of modern topology. A topological space is a generalization of the notion of an object in three-dimensional space. Hausdorff space in mathematics, type of topological space named from the German mathematics Flex Hausdorff. In topological space is a generalization of notion of an object in three-dimensional space. Flex Hausdorff. Definition of Hausdorff. A Hausdorff space, separated space or T2 space is a topological space where for all any two distinct points there exists neighborhood of each which are disjoint from each other. Point x and y in a topological space X can be separated by neighborhoods if there exists a neighborhood U of X and a neighborhood V of Y such that U and V are disjoint. U intersection V is equal to phi. X is a Hausdorff space if all distinct points in X are pairwise neighborhood separable. The condition is the third separation axiom after T0 T1, which is why Hausdorff space are also called T2 space. The name separated space is also used. This is the example of Hausdorff space. For every x and y in X with x is not equal to y, if there exist open neighborhoods U of X and V of Y where U and V are disjoints, then x and tau is called a Hausdorff space. Example of Hausdorff space. Prove that if x and tau is a Hausdorff space, then for every x belongs to X, the singleton set X is closed. Suppose that x and tau is a Hausdorff space and let x belongs to X. We will show that x by x is therefore open. Let y belongs to x by singleton x since x and tau is a Hausdorff. There exist open neighborhoods of U of X and V of Y such that U intersection V is equal to phi. But since x belongs to U, we must have that x does not belongs to V, so y belongs to V contained in x by singleton x. So for every y belongs to x by singleton x, there exists a v belongs to tau such that y belongs to v contained in x by singleton x. So in x by singleton x is equal to x by x, that is x by singleton x is open and so singleton x is closed. Now we discuss about Hausdroffness. Hausdroffness is one of the most important properties of the topological space. In fact, a number of texts assume Hausdroffness as one of the axioms that any topological space must satisfy. Compact subsets are closed. One of the most frequently uses of the Hausdroffness assumption is that compact subsets of a Hausdorff space are closed. Hausdroffness is not a necessary condition for a compact subsets to be closed. In general, a topological space for which compact subsets are closed is termed a Kesey space. However, Hausdroffness is particularly the most common way of ensuring that compact subsets are closed. Hausdroffness is not a necessary condition for sequence to have unique limits. A topological space in which every sequence of a points have a unique limits is termed as US space. However, Hausdroffness is particularly the most common way of ensuring that sequences of a points have unique limits. Limitations of Hausdroffness: if we build a space whose local models are Hausdorff, the whole space needed not be Hausdorff. This is because Hausdroffness is a global property. Thus, it is possible to build local Hausdorff space which are not Hausdorff. There are some external rings related to my presentations and there are some references. More E. H. Smith's HL, a journal theory of limits, and Josie Kedy, Introduction to General Topology, and some. Thank you and be safe. Stay at home, stay safe.